Hello, everyone. Thank you for coming. My name is Jessica Transick, and I just wanted to say it's been a great pleasure and an honor really to co-organize this panel with Paul Joskow, who has written a number of seminal papers in energy systems. I'm a professor in the Institute for Data Systems and Society here at MIT, and my work and my group's work focuses on developing data sets and mathematical models to identify and optimize combinations of technologies that can be used to rapidly transition energy systems away from carbon-emitting technologies and systems. And like Paul, I've worked across many of the different technologies that we'll be discussing today. And I should mention also, in addition to your seminal papers, Paul, you've played many other roles in advancing research and practice in this area. So as Paul mentioned, one of our goals with the symposium is to help accelerate progress on addressing climate change by focusing on and having a public conversation around a few examples of recent progress and also hopefully identifying future priority areas for both research and practice. In this first panel, we'll cover solar energy, which is one important tool in our toolkit for decarbonizing the electricity sector. And solar energy provides one of the most striking examples of success, actually, in government policy, industry, and researchers working simultaneously to improve and bring down the costs of a low-carbon technology. And costs are important when we talk about carbon emissions and climate change, because we need these energy services like electricity to be affordable for all people to support human well-being. If I could have the slide. Solar module costs have fallen by 99% over the last 40 years and about 90% since the year 2000. And these impressive trends came about because of various changes. If I could have the next slide, please. Yeah, there we are. In this technology. And you can see some of the cost components here. However, further cost declines are needed, particularly if solar energy is to provide a large share of electricity, because to do that, we need to add other support technologies to solar energy, which fluctuates in its availability. Those support technologies include things like energy storage, software and hardware to manage electricity demand, and an improved electric power grid. And these other support technologies add additional costs. So to compensate for these costs, it is important to keep aggressively driving down the costs of solar energy by reducing the construction costs of solar energy installations and reducing the solar panel costs themselves. And we want to do this in such a way that these technologies can continue to grow. And so we should do this using materials inputs that can scale. And while there's room for growth in the solar technology that dominates currently, which is based on the material crystalline silicon, there are other technology options that may offer even greater growth and cost reduction. And these are technologies that can be installed in new ways, for example, on building facades and in wearable devices. And these are technologies that use ultra-plentiful and low-cost materials. And our panelists today have been leading the way in developing these new and improved technologies for solar energy conversion. Their names are Vladimir Bulovich and Munji Bawendi, and it's a pleasure to introduce them briefly. Vladimir Bulovich is a professor of electrical engineering at the Massachusetts Institute of Technology here at MIT, where we find ourselves. He directs the Organic and Nanostructured Electronics Laboratory and is the founding director of MIT Nano, which is a new 200,000 square foot nanofabrication facility that opened in the summer of 2018. He's the author of over 250 research articles and an inventor of over 100 US patents, many of which have been licensed and utilized. And because of his passion and skill, I would say, in teaching, Vladimir has been recognized with MIT's highest teaching honor, which is the McVicker Fellowship. Munji Bawendi is the Lester Wolf Professor of Chemistry. His interdisciplinary research probes the science and development of chemically synthesized nanocrystals. He's been at the forefront of science and technology of semiconductor nanocrystal quantum dots for over 2 decades, and he's published as well over 250 papers. on quantum dots and other material systems. He's helped to support and start 4 companies in commercializing quantum dot technology, and he's a fellow of the American Association for the Advancement of Science, a fellow of the American Academy of Arts and Sciences, and a member of the National Academy of Sciences. So it's great to have them here to talk about exciting recent developments in the area of solar energy technology. And the way this panel is going to work is that I'm going to ask them a question, and if you could please come and join the stage here. And I'll ask them for an opening statement, a 5-minute opening statement in answer to this question. And then we'll turn over to you, the audience, and ask for your questions. So please do remember to, and if we could maybe put up that slide with the number that they need to text with their questions. Please do text those questions. Okay, Vladimir, so let's start with you.
Okay.
And yeah, let me tell you the question.
Oh, okay.
So what are some of the most consequential recent developments in the area of solar energy, and what are some of the most important unsolved problems remaining in this area?
All right. Well, thank you, Jessica. Thanks for asking, because it turns out the answer to the question is never straightforward, meaning there are many different ways to address what is facing us, that is to come up with a way to decarbonize. Munji and myself are very passionate about solar, and if I can have the slides coming up. The way we are thinking about solar technologies is really to look at where they're being deployed right now. And you can find them in 3 particularly big markets. Utility systems, the ones that cover large area fields, maybe on top of your roof as rooftop residential systems. Or if there's a large commercial rooftop, you might find them there. The one thing you might notice if you look at these images, in each one of them, the color is a dark blue. That's because these are all silicon panels being installed on top of all of these systems. Why would the silicon be the only answer? Well, the answer is that there are many different answers to be given. But silicon has been around for a long time. We have perfected it. We've done an amazing job in reducing the cost. If you do look at that reduction in cost that Jessica was pointing to, it is all about perfecting this particular silicon technology that now gave us a benchmark to think about how to go beyond what is the usual way of making solar cells. So what could be beyond the usual way of making solar cells? Well, the one big challenge of the silicon cell is actually the weight of the cell itself. That doesn't sound like a significant thing to point to, but actually it turns out is the key to the challenge of making installations. I need to reinforce that roof if I'm going to put up on it a 50-pound, 4-by-6-foot solar cell. If I put multiple of them, I definitely have to reinforce my roof, or at least put an aluminum structure underneath to be able to accept it. Every one of those 50-pound solar panels will also need to be picked up by a laborer. Well, we better not make the panel any heavier than 50 pounds, which means if I want to cover a large enough area, I'll need to tile many panels next to each other, wire them in the field. Wouldn't it be nicer if I had a lighter cell, one that I could actually unroll, kind of unfurl as a carpet almost, and maybe add to it even a microinverter, so that the DC electricity made by the solar cell can be directly converted to AC electricity. And really all that you have is go to Home Depot, buy the carpet called solar cell that weighs maybe 10, maybe 100 times less than silicon per area, unfurl it and staple it to your roof, and have a plug that you simply plug into because it's going to give you 110 volts coming out anytime the sun shines. That would be a very different way of thinking about solar electricity. And solar electricity today already reaches remarkably low prices. You can buy solar, well, below 5 cents a kilowatt hour. 3 cents a kilowatt hour are even some of the spot prices that have been suggested. In Massachusetts, we pay about 16 cents a kilowatt hour. If you're in Arizona, you pay about just north of 10 cents a kilowatt hour. Indeed, solar can provide you very cheap, unsubsidized electricity. Now, it needs storage, because you need to use it right away, and next panel will discuss the storage itself. But one thing that is needed is to reimagine the format of the cell. So in our labs, Munji's and my lab, we think of different ways to indeed advance that format redefinement. This would be, in the next slide, an example of one of those opportunities. Do this. One of the ways to go ahead and make a solar cell is to make it actually just out of the material that needs to absorb light. In that case, your cell can be as thin as about 2.5 microns. Now, mind you, I just need to give you some scales. A wafer of silicon is about 150 microns, which is about 1.5 thicknesses of human hair. Remarkably thin in some ways. But you can scale it all the way down to 2 microns, and then this, what used to be a silicon wafer that is brittle at 150 micron thickness, becomes a thin film that happens to be made of amorphous or polycrystalline nanostructure materials, not silicon, that absorbs light really, really well. And as a result, if grown on a 1 micron substrate, you can think of this as a saran wrap with a thin solar active film and a saran wrap layer on top, you can make a 2.5 micron thick structure that is light enough you can rest it on a soap bubble. And these are some of the examples of what we've done, just as an extreme way of showing extreme opportunity in rethinking what a solar cell is. We have, in the times past, taken some of these technologies and actually recently added them to fabrics, because it turns out a solar cell like this is awesome, extremely light, generates 6 watts per gram of the solar cell, but it's extremely fragile, as it's only 2.5 microns thick. Adding it on a 25 micron thick fabric makes it impossible to break, and at the same time, extremely light. This would give you a factor of 10 to 100 times less weight than silicon wafer does. Where would this really matter? Well, there are many places you can imagine a technology like this mattering. One place would be indeed in developing world, where deployment of the cell is a big challenge. Being able to actually deliver the solar cell to your village sometimes is more important than most of the other metrics. And how do you deliver the cell to a local village? Well, carrying it on your back. If you have a more efficient cell, you'll carry more watts on your back. If you have a lighter cell, you'll carry more watts per kilogram on your back. And as a result, for a load of 50 pounds or such that you might be carrying, you'll deliver a lot more power to your village, no matter how efficient it is. It needs to be reasonably efficient, but not the ultimate efficiency. Weight is one of the metrics that we consider. Another metric we consider is redefining the format of the cell so it looks nearly invisible, as integrating solar into everyday design maybe is the key to putting solar on any surface we ever touch. This is a version of a cell that uses nanostructure materials, molecules, that are designed not to absorb visible light, but to absorb infrared light, and as a result, generate electricity that we see here. This particular version, in this point, is being commercialized by a little startup called Ubiquitous Energy. They're looking at ways of scaling this technology from this small panel size to something that could actually power your conference space. So here is a picture of the recent installation from October 2019 that indeed is outfitting a particular conference space to power it with lights as needed, and indeed offset the energy footprint. Those windows are those solar cells. You don't see them. There's not much to see, and that is indeed the whole point of recognizing an entirely different way of deploying solar power. This is one way to do it on the sides of the buildings, and if you had the solar cell facing south, you can collect a good fraction of light, even if it's vertical. If you have one facing east, another one facing west, you would collect just about as much energy as a horizontally laid down solar cell that collects only the zenith sunlight coming down. It's a very different way of thinking of what solar could be. And in such instances could open entirely new markets of launching different kinds of solar technologies. But beyond everything I just showed you today, we also strive to reach very high efficiency, again, using new nanostructure materials. My colleague Munji Bawendi is a world expert in redefining the scale of materials and then using them to take that next step. And so I'll ask Munji to tell you more about the Perovskite technologies.
Great, and just while we're transitioning there, please keep your questions short or they get cut off from poll everywhere. So that's just a reminder.
You need to advance it here. Yeah.
Okay, well, thank you very much. Thank you, Jessica and Vladimir, for introducing the subject. Silicon is a wonderful material, as we've seen, and the costs have gone down tremendously, and the deployment has increased exponentially at an incredible rate. And so when we think about new materials that are potential replacement for silicon, it's a huge challenge, huge technical challenge, and a huge commercial challenge as well. And I would think that one of the challenges of any new material coming up today is that death valley between making things on a small scale to getting up to high enough scale that the costs come down enough to begin to be competitive with silicon, even though they may have incredible other performance aspects beyond silicon. That death valley is something that I think we're going to have to really think hard about how to cross when we talk about any new material. And so the material that I'm going to talk to you about are perovskite thin film photovoltaics that emerged on the scene 5-6 years ago, suddenly. It reminds me a lot of the way that blue LEDs emerged in the 1990s. After decades and decades of people trying to make blue LEDs out of zinc selenide, without any luck, they wouldn't work only at cryogenic temperatures. Suddenly, gallium nitride came along, and we have blue LEDs powering our electricity today. And so the perovskite thin films remind me a little bit of that. They came across a few years ago, as I mentioned, and then suddenly they displaced a lot of people's research that were doing on organic photovoltaics, which had been slowly getting higher and higher over decades and decades, but it wasn't clear that they were ever going to get high enough to match silicon. And today, perovskites are within striking distance of silicon. So there are a number of interesting aspects to the perovskite photovoltaics. Just like organics, they're easily, this isn't. It's not showing up here.
Oh, it's showing here.
It's showing here. Here we go.
There
okay.
we go.
There's a lag. Okay, let me not touch anything. It's solution processable, which means that you can do things at fairly low temperatures, less than 150 degrees Celsius. You can do things roll to roll, like you print a newspaper, potentially. You can do things at very high speed when you print newspapers. You can tune the band gap, so this idea that Vladimir pointed out of having something that's just not blue, like silicon is blue, but having different colors, maybe somewhat transparent, become accessible by changing the material composition of these very thin films. The optoelectronic properties, and I'll just focus on one here. It's extremely absorptive. It's about 100 times more absorptive than silicon, which means that you can make it 100 times thinner than silicon and still absorb the same amount of light. And that's part of the reason why we can go to these extremely thin films, like the one that Vladimir mentioned. And as a result, because it is so absorptive, you can think about the power per weight. In this case, 25 watts per gram compared to silicon, which is on the order of a watt per gram. So 25 times more power per gram than silicon. And that opens up a lot of possibilities. Okay, this is what the structures look like. You've got the perovskite thin film itself is just less than a micron, it's a few hundred nanometers in thickness. The whole device is about a micron in thickness compared to hundreds of microns for a silicon device. And we can make them out of solution, or, and when I say we, I mean that there's a huge community of people now working in this area throughout the world. We happen to have gotten lucky at MIT and hold the record today for the power conversion efficiency at 25.2%. And just to keep it in perspective, silicon, the best silicon research cell in the lab today is the blue dot right above it at 26.1%. So we're so close to the best that silicon can do. And silicon has been at it for 40 years or 50 years. And this has just been just a few years. And there's no reason why this record is surely going to be fleeting. And next quarter, because these are updated every quarter, I'm sure somebody else will have the record. It'll be a little higher. And within a year, I'm sure it's going to pass silicon. But there are challenges for any of these. I mentioned the challenge of scaling up. How do you go from making things one-off or in small scale, even if you manage to make reasonably large modules in research lab, so that the costs come down enough so you can have a picture like the one that Vladimir showed earlier with a field full of these cells. Because that's the scale that you need to go to for the cost to come down to be competitive. So that's one huge challenge. Another challenge is, when we do a cost analysis, the material, because it's so easy to make, it's also easy to fall apart. And it has issues with water and oxygen, and those may sound really terrible, but when you think about it, your cell phone, if you've got a Samsung phone or iPhone 10 or 11 that has an OLED display in it, when the OLEDs first came out, they didn't last very long. They were sensitive to water and moisture, and today their lifetimes are essentially forever, and we don't think about it. They're completely deployed. So it's an engineering problem that can be solved, and as we solve it, the cost also will come down. If you look at the cost of components in one of these things, this is the main cost. It's the encapsulant. Everything else is, this is the cost of the absorber layer, of the material itself. It's less than a penny per watt. It's less than 0.2% of the whole cost of the cell. So it's not the material itself. It becomes these extra costs here. So when you compare, let's say, the cost of silicon compared to one of these today, most of it is how do you keep it intact? That's an engineering cost, which through scaling will come down. And as we think ahead also, there's the issue of the EH&S. This was an issue also when in my own work on quantum dots, when they were started to be deployed in televisions. They contain heavy metals. It's regulated. There was an alternative, but it would have required, from an academic perspective, a tremendous amount of work, and there was no motivation in the academic community to actually fix that EH&S problem. Nobody would want to pay for it. But it took Samsung to decide, okay, this is a really interesting material. They had the resources. They were able to get rid of the heavy elements to replace them with less toxic elements or non-toxic elements. And because they had the resources and the will and seeing a market, they were able to then create the material that was up to par. And today you have Samsung TVs that have quantum dots in them. We are in the same position today where these materials have lead in them. And if you look at the content of lead, and you can do a regulatory analysis on them, you can see that in the European Union, if you put your perovskite on a glass substrate or on a flexible substrate to make it light, you're above the regulation. So you have to work on that somehow. In the US, I lost the. There it is. In the US, it's the amount of lead that leaches when you dispose of it, and we talk about lightweight, which means a light substrate, but the cost of disposal and the hazard is measured by the percent by weight of lead that leaches. And so by going to lighter weight, you actually make the material more and more regulated. And so and so we have to figure out how to fix this, either by encapsulation layers to entrap the toxic element or the lead that's in here, or by remove the lead. And in the academic community, there are already people working on getting rid of the lead. But it's going to take, the challenge is going to take the resources to be able to do this on a large scale. And I'm going to end on this note.
Okay, great. Very good. Well, I think it's really exciting to hear about this work and the fact that you're incorporating considerations of recyclability. There was an audience question about that. Toxicity, scalability, construction costs into the design and the early stages of design of this technology. That's something that's changed over the last decade. I think that's a really important movement and development in this area of research. So we don't have much time, and I want to make sure we have time for the storage panel, but just very quick couple of words on, one of the questions was on government support for research, and there's the saying, the all of the above strategy. I see Ernie Moniz in the audience there, that we don't want to get locked into just one technology. We want to make sure that we're investing in a diversity of technologies. That's very important. But of course, there are always limited financial resources. Are we putting all of our eggs in one basket, or are we doing enough to, at the federal government policy level to advance a diversity of technologies? In your opinion? And I guess just to make it a short question, do you feel optimistic about the market entry of these technologies you're working on?
So I think I'll attempt to answer it the following way, which is that if what Munji and I are presenting up here becomes real, the cost of electricity coming from solar might go down by as much as factor of 3. So since the well-being of a human living in a particular country is directly related to per capita energy use, the more energy I can give to a particular individual, the better off they'll be. If I can reduce the cost of electricity by a factor of 3, whichever country is the one that's controlling that capability and that resource has a leg up over the rest of us. So I do think it is an important element to spend investment in, and indeed, US government's contribution to that is relatively small compared to what's going to be truly needed to scale up the technology, but absolutely essential in giving us the head start in being able to prove viability of some of these solutions.
I agree. There's no replacing federal funds for this kind of research at the fundamental level. Companies come in once they see the proof of concept and path to market. That's 5 to 10 years away. But a lot of this stuff was done purely with government funding.
Another way to put it is if companies are going to sponsor us, they need to be profitable. There are not that many profitable solar companies in the world, not mind the United States. So their ability to indeed invest in a fundamental research is limited, although they are trying. But you don't see that reaching into academia very often.
Okay, good. Well, thank you so much. And let's transition now to the storage panel.